All right. I'm so happy to introduce our first speaker, Allyson Ettinger, who is an assistant professor in the Department of Linguistics. And prior to joining Chicago, she spent a year as a research assistant at the Toyota Technological Institute at Chicago, where she maintains an affiliation. Dr. Ettinger is a computational linguist addressing research problems on language in humans and machines. Her work combines her backgrounds in linguistics, natural language processing, and cognitive neuroscience of language to conduct innovative interdisciplinary research. She also strives to help build community across these domains, by collaborating broadly across these fields, teaching interdisciplinary courses in them, and leading workshops that bring together researchers from linguistics and computer science. Allyson completed her PhD in linguistics at the University of Maryland, and prior to that spent 2 years conducting neurolinguistic MEG research at NYU. Prior to that, she received her bachelor's in linguistics and psychology from Brandeis University. Allyson is no stranger to CDAC Summer Lab, where she was a mentor last year on a project seeking to make machine learning more human by examining parent-child language alignment using neural language models. We are so delighted to welcome Allyson back to the CDAC Summer Lab community today. So please join me in welcoming her to our virtual CDAC Summer Lab stage. All right.
Hi, everyone. Should I go ahead and share my screen now?
Yeah, go for it.
All right. How is that? Are you seeing this?
Yes, looks good.
Perfect. All right. Let me also go ahead and minimize the faces. Hi, everyone. Thanks so much for having me. This is a great program. As Katie said, I participated previously, and I hope that everyone is having a great summer. So I'm just going to talk briefly today about one project. Before that, I'm going to, as Katie suggested, give you just a little bit of information, though you heard a fair amount about my background just now, give you just a little bit of a description of how I got here. Since I agree with Katie, that can be interesting for folks who are getting a sense of what they want to do and how they're going to get there. So, all right, let's go. So how did I get here? So around middle school, I became very interested in languages, and this is by no means the only way to become a linguist. I want to make sure that that is clear, but in my case, this was true. I did get interested in learning languages, and that was why I ultimately, as my first major in undergrad, decided to try out linguistics, and I liked it. And then I was advised by the internet that I shouldn't only major in linguistics. I should probably pair it with something else for sort of a more robust major. And so I ended up adding on psychology as a secondary major. And so this ended up being the foundation that I was building on in my undergraduate education, was sort of a focus on language and the human mind. And my undergraduate thesis, I was very interested in the meaning of language, and my undergraduate thesis was focused on a single utterance final particle, discourse particle in Mandarin, and what you see here, this is the particle ba, and I was watching TV shows and movies in Mandarin and extracting usage of this particle and analyzing it. And that was the type of linguist that I was as an undergraduate. Now, I almost left out this part, but I think it's relevant to know that people's after their career often is not a straight line. So I had been encouraged to go to grad school as an undergrad, but I wasn't sure that that was what I wanted to do, wasn't sure that I wanted to make that type of commitment. So I ended up going back to China. I had gone previously also during undergrad for study abroad. And I spent a year doing something completely different, completely irrelevant to what I now do and irrelevant to what I did in undergrad. And I was studying things, economics and law and political science at the Hopkins Nanjing Center in Nanjing, China. But while I was there, I really realized that I missed studying the brain, studying humans, and studying how language works. And so I ended up going back to the US and getting a job at the NYU Neuroscience of Language Lab, using magnetoencephalography to study how people's brains respond to language inputs. And so at this point, I'm getting fairly interested and fairly experienced in studying how language works in the brain at a neural level. So I decided, I think research is a fairly reasonable and interesting path for me to take, an appropriate career for me. So I went ahead and did my PhD, as Katie said, at the University of Maryland in linguistics. And it was there that sort of the final piece of the puzzle, I had already become very interested in how meaning works in language, already had become interested in language in the brain. The final piece of this puzzle was that I became very interested as a graduate student in computational methods for approaching language, both computational methods for modeling how language works in the brain, and also trying to engineer computational methods of processing language for artificial intelligence purposes. So that's how we bring us to my current research program, pulls together all of these different things. What my research does essentially is it looks at language as it operates in the brain, looks at language that we're trying to engineer in computational systems, and brings together in an interdisciplinary way insights and methods from both of these different fields to try to have a interactive and interdisciplinary type to both of the fields. And the paper that I'm going to be talking about today, I think, is a very good example of this type of approach. The paper I'll be talking about is called What Burt Is Not, Lessons from a New Suite of Psycholinguistic Diagnostics for Language Models. And this is going to be focused on examining an artificial intelligence model using methods from psycholinguistics that are used to study language in the brain. All right, so let's dive right into that. I know we don't have a ton of time for my segment here. So let's, as a brief introduction, I don't know how familiar all of you folks are with these topics, so we're going to start zoomed out of a little bit. As some of you may be very acquainted with already and some may not, recently within the field of natural language processing, this is the language corner of artificial intelligence for anyone who's unfamiliar, we've seen some really impressive successes. For instance, a famous one, these output from GPT-2, where they gave the prompt to the model and then it continued with this text. And people were really, really impressed by this. There are some sort of semantically odd things. For instance, a four-horned unicorn doesn't make sense. But setting that aside, it seems quite coherent. It stayed on topic for a long time. People were really impressed by this. So these successes, in large part for the past couple of years, these really impressive successes have largely been driven by what's often referred to as pre-trained language models. And these are models that are trained on a ton of data, primarily to predict words in context. So you might have a model that's being given text from left to right, word by word, and its job is to predict the probability that, for instance, the next word is going to be banana. Or a model, and this is going to be the paradigm of the model that we'll be talking about in this talk today, you might have bidirectional context provided to the model and a mask for the word that you want the model to predict. Again, in this case, you can probably tell that the likely completion here is banana. And the idea here, or at least empirically what seems to be the case, is when models are forced to become at predicting words in context, they seem to be able to pick up on a lot of information about language and abstractions about language that allow them to be better at making predictions of words in context. And because these models have been so good on so many tasks, people start really asking quite seriously, have these models really learned some serious stuff about language? Do they really understand what's going on? How much is it? How much linguistic competence have they really obtained? So this is the question I'm going to be focused on here, is trying to get a clearer sense of how much sophisticated linguistic knowledge these models really have managed to capture as a result of their pre-training process. That, again, because it seems like they have picked up on a fairly intelligent set of abstractions that allow them to perform well on tasks. And relatedly, how do these models' language capacities compare with language capacities and behaviors that we observe in human cognition? Because humans really are the gold standard when it comes to language. Language is a uniquely human trait. So the way that we're going to go about doing that, to study, ask these questions about language competence in these models, is we're going to go ahead and study them in their natural context of predicting words in context. So what we're going to do specifically is we're going to take some contexts like this one. We're going to incorporate in these contexts certain types of information that would help the model in making a prediction if it is able to process and make use of that information. So for instance, in this case, in order to make a prediction of what's going to go in this blank here, you as a human are able to make use of the fact that there seems to be a party going on. This person is not eating soup. It seems like she already does have the soup in front of her. What do you use to eat soup that you would be critically missing and it might explain her not having it? Probably the answer is a spoon, right? But there's a lot of processing that goes into that. You don't think about it too much because you are extremely good at language, but it's not a given that the models will be able to do this. So we're going to use these types of tests to test how well the models are able to make use of this information to make predictions in context. And as it happened, this is exactly the type of paradigm that is often used in psycholinguistics for studying how language works in the brain. You give humans a context that includes a certain amount of information, and you see how the brain responds to words that arrive in that context. You see how surprised the brain is to ask questions about how and when certain types of information are being processed as the brain is understanding language. So we're going to take advantage of that fact, the fact that these types of tests already exist for studying the human brain, and we're going to use specific types of tests to test the models. That is, to be precise, we're going to choose cases where humans are able to make very good questions when they do a fill-in-the-blank task. This is called a closed task. And it doesn't involve any time pressure. So we're going to assume that this involves all of the humans making use of all of the context information. And then we're going to also choose cases specifically where not only humans make good predictions on the fill-in-the-blank task, but their predictive responses in the brain, specifically one called the N400, seems to be missing key information that would inform word expectations, but in the case of this brain response, isn't. So the reason we're going to choose this type of case is that it's going to allow us to target this particular type of challenging predictive information that the N400 brain response is missing and test whether these predictive language models are going to manage to represent and use that critical information that the brain sometimes misses, but that humans are able to pick up on given enough time. We choose specifically 3 data sets. They're going to test these types of linguistic capacities. I'm going to go over them in detail in a moment. But we're going to be focused on 3 types of analysis. The first is word prediction accuracy. We're going to be just looking specifically at how well can the model use that information in context to make correct word predictions in its top word predictions. Just checking the time. Sensitivity tests, we're going to say how well can the model distinguish between good and bad completions in the context. So we'll give 2 or 3 completions and see whether the model can tell which one is better. And qualitative analysis, where we'll just examine the completions that the model prefers and see what it can tell us about how the model is processing the context. We're going to be studying a model called Burt. For many of you, this may be a very familiar model. For some, perhaps not. At the time that this paper was written, this was the primary model that was an example of these impressive types of models that could that we wanted to study. So we're going to look at 2 versions, a smaller and a larger Burt base and Burt large versions. And we're just going to be doing something that's very natural for this model after its pre-training. We're going to be masking this target position, and then we're going to be looking at Burt's probabilities in that position. All right, so we're going to go take a look at what we find by subjecting the model to these diagnostics. The first diagnostic uses sentences like the one that you saw here. The idea is that you need common sense and pragmatic inference to discern what situation is being described here. You need to be able to know, what do you usually eat soup with? Why might one not be eating soup? You need to be able to infer the fact that some soup. So it's not that she didn't have a soup yet. It seems to be that she doesn't have a spoon. It's a fair amount of processing involved. So for the accuracy test, what we're going to be doing is just saying what proportion of the time is the correct item, in this case spoon, in the top K Burt predictions. And we find that the model is doing decently. When we look at the top 1 prediction, the smaller model about 1/4 of the time is getting the correct answer, the larger model about 1/3 of the time. And when we look at the top 5 predictions, about half the time, the model is with the right answer. Now we wanted to check a couple of perturbations, because in some cases, it might not be that the model really needs to use all of that information that we as humans are using. It might have some shortcuts that it can use. So we tried a couple of things. First of all, we shuffled the words in the first sentence to see whether the model really needed the whole sentence or if it was just using some keywords. And secondly, we truncated the second sentence so that it only had access to the final 2 words leading up to the target position, just in case those final 2 words were particularly informative and it wasn't really using the whole sentence. We see that there is certainly a drop in accuracy. So in many of the cases, it was making use of these different types of more sophisticated structured information. And when we combine the 2 perturbations, the accuracy gets even worse. But we do also see that there's still a non-trivial amount of proportion of the items that the model is still getting correct. So in some of these cases, they might not be quite as hard as we would like. So we'll keep that in mind. For the sensitivity test, we're going to compare how well the model is able to prefer the correct completion spoon over 2 semantically related completions that are not appropriate in the context, like knife and bowl. The model is, in fact, a solid majority of the time, it's preferring the good completion to the two bad completions, though we note by imposing a threshold of 0.01 on the margin between the probability, that in general, these probability differences are quite small. We don't want to read too far into this, but the main point we want to make here is the differences are quite small. Finally, looking at this qualitative analysis, we're just going to take a look at some of the harder items, some of the mistakes that the models make. What does that seem to tell us about how the models are processing things? So we see this. Pablo wanted to cut the lumber he had bought to make some shelves. He asked his neighbor if he could borrow her. We see a set of things that someone might very reasonably borrow from someone, but they really don't have anything to do with cutting lumber. Similarly here, the snow had piled up on the drive so high that they couldn't get the car out. When Albert woke up, father handed him A. We have a set of pretty unrelated things, sometimes fairly amusing, that have nothing to do with shoveling snow. So we see a bit of a pattern here. The model is able to pick up on some things that are reasonable based on certain parts of the context, but aren't making use of all the information. I'm not going to dwell because I know I'm running short on time. I'm just going to give you all a sense of what we get out of the final two diagnostics. So the second diagnostic is drawn from a role reversal paradigm in psycholinguistics, where we have sentences like the restaurant owner forgot which customer the waitress had, and we switch these nouns, restaurant owner forgot which waitress the customer had. If models are not very sensitive to things like semantic role, who does what to whom, in what types of events, and knowledge about typical events and their participants, then they're going to struggle with these subtle differences like this. And the N400 indeed does struggle with that, and has trouble differentiating between these two. For the accuracy test, we're just going to be testing again whether the model top predictions match the human top prediction in these two different types of contexts. We see that the model does not do too great here. The accuracies are generally lower than we saw in the previous diagnostic. And when we do perturbations where we remove information from one or both of the nouns, we see again that the accuracies do decrease. But if we look carefully, we see that it's mostly in Burt large that we see substantial decreases in accuracy. For Burt base, we actually see not too much of a decrease, suggesting that Burt large is making more use of the combined information of the two different nouns. For the sensitivity test, we're going to be comparing across these two contexts. What proportion of the time does the model assign a higher probability to served in the correct context over the incorrect context? We find that an even higher proportion of the time is doing well on this. It is able to differentiate between the two different word orders. But again, when we impose that threshold, just as kind of a reality check here, those margins are very, very small between those probabilities. So the sensitivity is there, but it's small. Qualitative analysis, basically what these examples show is that Burt base, including examples like killed and bitten, whether the girl is the agent or the bear is the agent, whether the girl is doing the doing or the bear is doing the doing, but large has sort of sorted these two things out and includes those only when the bear is the subject. But in the case of the restaurant, the customer and the waitress, we do see that served is the top completion regardless of the word order. So there's certainly room for improvement. Final diagnostic, and this is the one that really gives the most interesting outcomes. Here we're going to give the models really simple sentences like a robin is A and a robin is not A. And we're going to be testing the model's ability to handle things like negation. For our accuracy test, we're going to be focused on the affirmative. We're going to be testing essentially, if we give the model a robin is A, is it able to retrieve what we refer to as the hypernym, the correct category that the robin is part of, in this case, bird. We're going to ignore the negated case for now, because as you can probably tell, a robin is not A is not a very predictive context. We can't really say what the correct answer is there. So we're going to ignore that for the accuracy test purposes. And what we see is that the models, when we look at the top predictions, they're extremely good at retrieving the hypernym. When we look at k=1, we have lower accuracies, and examining the outputs, we can see that this is exclusively because the models also like to complete the contexts with something like a robin is a robin, which of course is true, but is not a particularly useful sentence. Now we move to our sensitivity test, and this is where we finally look at the impacts of negation. Here we're going to be testing, in the affirmative context, can the model assign a higher probability to the true continuation bird over the false continuation tree? Critically, when we add negation, will the model assign higher probability to the now true continuation of tree over the now false continuation of bird? And when we look at the results, it's a very stark pattern. In the affirmative case without negation, the model is assigning a higher probability to the true continuation 100% of the time. But in the negated context, it's assigning a higher probability to the true continuation 0% of the time, suggesting a strong insensitivity to the logical impacts negation has on its context. We'll look at the completions. We see basically something that's consistent with what we just saw in the quantitative results. When we have affirmative contexts, we have some reasonable continuations, certainly not all true, but many reasonable continuations. But when we add negation, basically those continuations don't change, suggesting that the model is not processing much of an impact at all of that negation, even though negation has quite a substantial logical impact on the context. Summing up now, what we find based on these diagnostics for this particular couple of models is that the model seems to be decent in terms of sensitivity to role reversals and to differences within semantic category, though based on those sort of rough margin tests, seemingly a little weaker than the sensitivity that after those distinctions. Great in terms of retrieving hypernyms. I didn't talk much about this, but you can see from the qualitative analyses, also really, really good with determiners, grammaticality. The models are really good at producing grammatical continuation. But we do see that the model seems to struggle with challenging inference and event-based prediction based on the first two diagnostics. And based on the third diagnostic, we see a clear insensitivity to the contextual impacts of negation. To the final slide. Speculating about this a little bit after the fact, we can realize that, as it turns out, negation really is not often very useful for word prediction. And because these models are critically going to be only really learning things that are helpful to make them better at word prediction, it may mean that this type of pre-training is kind of fundamentally poorly suited for learning something like negation. So the questions that arise out of this are, first of all, what other aspects of language comprehension might have this property? What other aspects of comprehension might be sort of fundamentally poorly suited to being learned via a word prediction objective? And finally, what needs to be done in order to master these properties, preferably without losing all of the generality and sophistication that we did gain through using these types of pre-training? This is where you can find the data in the code. Thank you, and I will be happy to answer questions after Chenhao's talk.
Fantastic. Thank you so much, Allyson. Great. Well, without further ado, I'm going to introduce our next speaker, Chenhao Tan. Pull up slide here. Perfect. So, can you guys see the screen with Chenhao? Great. Okay. I will assume yes. So our second speaker today is Chenhao Tan, who is an assistant professor in the Department of Computer Science and is also affiliated with the Harris School of Public Policy. At UChicago, he directs the Chicago Human Plus AI, or CHI lab, which seeks to develop a synergy between humans and artificial intelligence through better understanding human behavior and interaction with AI. His research interests center around language and social dynamics, human-centered machine learning, computational social science, as well as natural language processing. He is a co-principal investigator on a recent CDAC Discovery Challenge project, shameless plug, which is titled AI-Driven Tutorials for Radiology Student Training, which really seeks to answer, through interdisciplinary approaches, the question of whether the success of using artificial intelligence for radiology diagnosis can help to train tomorrow's radiologists. Prior to joining UChicago, Dr. Tan was an assistant professor of computer science at Colorado University Boulder, and before that was a postdoc at the University of Washington. He received his PhD in computer science from Cornell University and his bachelor's degree in computer science and economics from Tsinghua University. Chenhao is joining us as a first-time mentor in Summer Lab this year, and we're so delighted to have him as part of the program, as well as today as a speaker. So please join me in welcoming Chenhao to our virtual stage.
Thanks for the very nice introduction. I'm just going to go ahead and share my screen. Does it work? Do you see the screen?
Yes,
okay, cool. Thanks. Yeah, it's very nice. The Allyson gives a very nice overview of AI, and mine more was continuation, but I'm not going to dive deep in any project. It's more like an overview of what's going on in the lab. And as Katie mentioned, my lab is called Chicago Human Plus AI Lab. So in short, CHI, if you like this particular kind of T. So this is an NLP session, and a lot of my work is about language. So we're going to start to think about the kind of how language fits into our society. And in particular, we can start from a case in hospitals. There are about 800 million visits per year in the hospital. And this was a statistic before COVID. Likely last year's statistic was much higher because of COVID, or maybe not. I don't have the latest statistic on that. But translating to language, that means at least assuming that one visit leads to one note, and usually it leads to more since you have many different types of notes written by doctors, nurses, and other types of caregivers. That's about 900 million number of notes, and that's about 2 million notes per day. And that's a huge amount of data, and it may contain very valuable signal for the healthcare or the quality of life for the patients. And this kind of analogy of like how we have this kind of language source that can potentially support decisions made by humans, and in this case, it will be medical notes supporting medical diagnosis, is very common across many different domains. For instance, here are some other examples in the justice system. You can get arrest narratives that can be useful for bailing and sentencing decisions, and loan applications that can be useful for loan approval, rejection, and resumes that are often used for hiring and screening decisions. At the same time, I think although a lot of my work is about computers, but I think there's more and more realization that automation is often not desired. In the justice system, this decision from the Supreme Court of Wisconsin says that a compass, which is a system that can be used for assessing people's risk for committing crime if they are bailed, should not be used to determine the severity of a sentence or when an offender is incarcerated. And more importantly, it says judges be made aware of the limitations of risk assessment tools. So a lot of this recent work that I have been trying to think about is to think about how we can use AI to serve as an effective aid. How can we leverage this kind of understanding that a Burt might have to help people in making their decisions related to language, for instance. And in this applications I was talking about, so this translates to AI plus doctor, AI plus judge, and so on. And in short, I think what I'm hoping you to take away here is that AI can only add value if humans know when and how to use AI recommendations. And this is kind of where this human plus AI lab comes from. And in this talk, I'm going to just use H plus M for most of this, to refer to this concept. And so that's kind of the goal of my lab. And generally, we are hoping to develop the best AI, not just period, but the best AI for humans. So it's not seeking some kind of intelligent, absolute intelligence, which actually often doesn't really exist in a lot of social problems, since people's value system can often change. What is good may not also be well defined compared to games like a chess game or Go, where versus losing is very well defined. And so far, we have been mostly talking about this augmented dimension, where we are thinking about the best way to incorporate AI into human decision-making process. And I'm going to kind of go into a little more detail later about this general direction. And the other direction that I also turn to work on is to think about how we can build AI to understand the language and people in social contexts, to understand what kind of language, for instance, is more effective for persuasion. And next, I'm going to kind of give a very quick, hopefully quick overview on different projects going on in the group. And I'm going to try to leave enough time for questions. So I may skip a couple of things depending on how quickly I go. So like a big part of my interest is what I mentioned, persuasion in general, kind of what makes an argument more persuasive, how we can better change someone's opinion. And another kind of very different idea is what I call idea ecosystems. And the goal there is to think about how different ideas relate to each other. For instance, like in the context of immigration, maybe the notion of like undocumented immigrants, illegal alien are somehow contradicting each other. And also like in politics, pro-life, pro-abortion has been kind of the main themes in the abortion issue. And they kind of have a very interesting, sometimes we refer to it as kind of arms race relation. Like when we see a stronger argument for, or a more growing popularity for pro-life, the other side will try to grow pro-choice. And so you kind of see empirically, they are kind of catching up with each other all the time. And finally, on the more human side, we also think about how people engage with different communities. And in particular, recently, I've been thinking about how communities emerge, like how new community may emerge on Reddit, for instance, if you are familiar with Reddit. And if you think about on campus, your campus life, like how a new student club emerges, was it splinter existing community, and at the same time, once the new community emerges, how do community norms evolve? Do they pick up a particular kind of language? Do they say something specific, that's different from other communities, and so on. And on the augmenting side, a lot of work is about explanations, and this is kind of very nice connection with what Allyson was talking about. Kind of having, when you have such a complex model like Burt, can you explain some decisions coming out from this model? And can we and what can be defined as good explanations? What are the properties of good explanations? And once we have explanations, how can we effectively incorporate them into human decisions? How can we help a human make sense of explanations? Or in often cases, we are also trying to make sense to just help people make sense of the prediction. Say the system predicts this person should be approved for a loan, why? And how to make sense of things like uncertainty in that decision. How confident is the machine learning system or the AI system in that particular decision? And the final part of this presentation is to kind of just do a very quick walkthrough of some project. We are going to start with persuasion, and maybe I can magically finish everything. So persuasion is kind of a very classic problem, and I guess typically people can trace this back to Aristotle, but I think it has always existed. Even I assume in the world of chimpanzees, they also try to coordinate with each other and convince someone that you should do this or that. But in practice, it's actually very hard to observe successful persuasion. And like, if we have time, or maybe you can do this sort of experiment with yourself. Think about the next time you change your mind on something, or you were convinced by someone, you should change your mind on something. And on the internet in particular, everyone seems to be very angry. And at the same time, I think there's this very nice community known as Change My View, which is dedicated to people changing each other's opinions. And in this community, actually, success rate is actually pretty high. 30% of time, people have been successfully changed their opinion because of other people's argument. So we did a lot of experiments to kind of analyze what makes successful strategies for changing successful arguments. And here I'm showing something that's a little simpler, where we only think about, we don't look at any counter arguments. The way that GMI works is that someone will write an explanation of why they hold a particular opinion. And we just look at that explanation or justification for one's opinion and try to think about whether malleable to changes, whether it would be possible for someone else to change your opinions. And what we found is that if we compare the usage of first-person singular versus first-person plural pronouns, and one example here is, I think there should be not a speed limit versus we think there should not be speed limit. Usually the people who use the plural version or we, they are much less likely to be changed. And this kind of connects very well with some existing psychology theory. Kind of the rationale is that if we use we, then we are kind of associating this opinion with someone else or with the group. And we don't take responsibility for this particular opinion that I hold here. It's much harder for other people to change this group's opinion versus changing one person's opinion. And that seems to also hold on this particular community called Change My View. And the second example I'm going to use is in the other direction, where we're going to think about how we can augment people and develop best practice for incorporating AI into human decision making. And here we're going to think about how and I realize Actually, I'm going to skip this example. But the visualization is quick. But roughly, I guess this particular class of explanations that I'm very interested in is known as counterfactual explanations. Roughly, the intuition is that if you have an original input where the model is predicted the loan should be rejected, we try to find the closest example where the model will give you a different decision. And the explanation will be in the form of, if you increase your income by 10,000, then your loan will be approved, and so on. You can check out more details at this link. I'm not sure whether we are going to share later, but I'm happy to share if you are interested. And finally, I'm going to kind of talk a little more about this human AI induction angle, where we are doing a lot more work on. And one particular kind of to think about what possible assistance one can provide with an AI model in the context of human decision making. And we can propose this spectrum between for human agency, meaning that people make decisions without any AI assistance, and for automation, meaning that AI make decisions without any human involvement. And here are some possible ways. For instance, we can show the explanations, we can show people explanations and the labels, and show the pretty labels and suggesting high accuracy. And then one very interesting finding we found, although overall it seems very hard to improve human performance in these tasks that we have been looking at, but it seems that this is reliable. That humans are somehow able to more likely to trust the machine predictions when they are correct. So the green bar here shows that if the machine prediction is correct, how often people follow the prediction. And the red bar shows that when the machine prediction is wrong, how often people follow the prediction. And usually people follow the green bar is longer than the red bar, and that means people are more likely to follow the correct prediction. But at the same time, you also see that people also follow wrong prediction more than 50% of time. That's why it's actually very hard for people to get a better performance overall with machine assistance in all of these challenging tasks that we talk about. And finally, I'm just going to 1 minute talking about this thing that's very different from everything else I do. This is a very more or less kind of qualitative work where we're trying to ask people questions to figure out what things AI should not do or should do. And we kind of build a data set of different tasks, for instance, recidivism or Bayesian decisions, or this may also include daily activities like brushing your teeth or kind of doing your chores for you and so on. And then we ask a series of questions in the categories of motivation, difficulty, and trust and risk. And then we hope to get a final conclusion from human, whether you want to dedicate this to AI or not. And in general, we find that people almost never prefer automation in any of the tasks that we ask them about. And machine assistance is also almost always valued. So people don't really want human only almost in every single task. This includes diagnosing cancer or very high stake tasks. I think we even have things like along the line of military directions in this queries. And even in those tasks, people prefer or people would like some assistance from AI models. And here are some tasks where they prefer human to be the main person. So it would be what I call machine in the loop, where human is leading the game. So they can be picking birthday gifts, responding to 9/11, serving or jury duty. And for things like people actually command AI taking the lead includes sports news coverage, buy, sell stocks, and movie and packing. And you can actually see the full list of tasks and kind of see our survey results on this website as well. That's all for my presentation today. And I just want to kind of highlight these people who did this awesome work. And if you are interested, you can go to the website of my homepage and my lab. You can kind of see more information about the work that I talk about and the actual people involved in these projects. Thanks all.
Wonderful. Thank you so much, Chenhao. So we are going to now open up to Q&A. And thanks to Allyson and Chenhao staying so well on time. We have lots of time for questions, which I'm looking forward to a good discussion. So students and folks joining, please feel free to turn your videos on, since this is the more social part and we are talking about humans and machines. We can bring some human elements. I think we have a question in the chat already, but if you are thinking of questions now, feel free to get ready to raise your hand, and you can ask questions live or slot them in the Zoom chat as well. So Daniel, would you like to ask your question to kick things off? Oh, let me allow unmuting. 1 second. There we go. Okay.
Yeah, I guess my question was kind of simple. I was just wondering, like, what is Burt? How does it work? And like, can it work for other languages besides English? Or
Yep. Great question. The simple answer is yes. You can absolutely, and people absolutely have trained Burt on other languages. At the time that I wrote the paper, I don't remember what the status was of multilingual Burt and Burts in specific languages, but the model itself is not language specific. Basically, it's just a large transformer neural network based model, and you just train it on a whole bunch of data. So you can train it on multiple languages, you can train it on one language. It's just being trained to predict words in context. And so, yeah, that's the basic answer there. If you have a follow up about sort of the implications, but yeah, that's the short answer.
I guess, yeah, I was just curious in terms of like non-written or spoken languages, like for like sign languages or just like only languages that don't have a writing system, like would it still work on like audio data or
yeah, so it's mostly set up for text. There are certainly models that may make use of similar mechanisms that could also process different types of inputs, but Burt typically is mostly just operating on text. Yeah.
Thank you.
We have a shy group today. Kyle is video off, but I will pull a Kyle and call on people if we don't get questions. I know folks have questions. Chimobi, go ahead.
Well, I had a question for, is it Chenhao?
Yeah.
At the end of the presentation, you said something about how people wouldn't want 100% automation, or that they want human hands in there at some point. So even if we do have the AI that can give suggestions or provide or be a guide, how do we expect the people to actually listen to the AI, or is there some sort of training they'll have to go through? Will they know specifically if like, okay, the AI is like probably right about this? Like, what are the like, how do we make sure that they actually are listening to the suggestions that the AI is giving them?
Yeah, that's a very good question. I guess maybe let me try to rephrase your question a little bit. I think in general, the goal is not trying to get people to listen to AI all the time. And I guess the critical question is to figure out how to guide people to interact with AI appropriately. And in some extreme version, it can be things as if there's clear right or wrong decisions here, then always follow when AI is correct and do not follow AI when AI is wrong. And that is sometimes known as kind of appropriate reliance. And generally, so far, what people are seeing is that whenever there's AI, what happens usually is over reliance. People will also trust the AI even if the AI is wrong. But when there's no correct and wrong, then I think the space is a little more murky. And I'm not sure like why you ask that question. So like, for instance, one scenario I had a student who is very interested in is kind of the space of creative writing. Say now there's more and more people actually write novels with AI systems. Like in fact, GPT-2 has a public demo called kind of writing with GPT-2 or something that you can write and then press tab and you can get some suggestion from the system. And if you don't like it, you can revise that. And in the end, for the final product, is that your novel or how you think about the authorship going on in that process? There's AI assistance. I think it's also kind of very interesting open question that I don't think there's a clear answer. And in that case, like, it's unclear what is the best way to incorporate AI, or what's how you define the successful integration between human AI in decision creation. And in that space, we also did some experiments. I think generally what we find is that having AI helping people, it doesn't really improve the outcome in third parties' perspective. So it doesn't make the novel feel better to me as a reader, but it makes the writer more satisfied with the outcome. So the writer feels like I'm doing something right. And obviously what we did was kind of slightly different outdated system. So it'll be cool to try to with Burt.
Okay, thank you. I was just trying to imagine or put myself in that situation where I'm working with that, although I'm definitely not a radiologist, but I was trying to just imagine the situation, but thank you.
Yeah, okay, I think, yes, I think for radiology, okay, maybe that helps clarify the question too, but I think in that case, also what I mentioned is kind of this kind of explanation can be an important way to moderate people's interaction with AI. Like say, I give you a prediction, say this person is predicted to have prostate cancer, but I also give you more information. Here is why I think this person might have prostate cancer. And this can happen in many different ways. And there's a lot of different methods that have been explored in how to do that. But at the same time, I think it's far from soft. And I don't think we have a good way of giving explanations in this context.
All right. We just got a question in the chat from Annie. Annie, would you like to read your question aloud?
Yeah, sure. So first, thank you both so much for the really interesting talks. I really learned a lot, and this has been like an interest of mine too. So it was great to like get to know more about the field. For Chenhao specifically, I was wondering, for the situations where there might not be a correct answer, or where like current technology and AI has been shown to replicate existing prejudices. For example, like AI used to predict who may commit a crime again, or which AI used to like determine who a good job candidate is. Could you talk a bit about how AI should or can be used in these situations, and like how to address these situations where like using AI may reinforce like current inequalities in society?
Yeah, this is a very good question. I think, I guess there are two parts of my answer. I think like there's actually a kind of group paper called Roles of Computing in Social Problems. I think that's roughly the title. I think at the most basic level, or at one level, would be that AI can at least help us think about what biases are on and try to formalize the issue of bias or fairness. And like a lot of these questions emerged, there have already been a lot of discussion, but I think AI kind of at least resurfaces them and may allow us to compare, for instance, one useful comparison is to compare AI's fairness or bias versus a human's bias. And in order to do that, you need to measure human bias in the first place. And I think this kind of dynamics, if it's developed successfully or healthily, in a healthy way, then at some point in the future, we'll have a very clear benchmark of human bias and AI bias, and that will help us actually answer this question in a more informed way, compared to just saying that this algorithm is biased. And it's not like the human is completely unbiased. And the second part of my answer would be that I think that's what one of my work is trying to think about too. Like I mentioned this concept of appropriate reliance. I think ideally we can somehow expose AI's bias, make people aware of AI's bias. And when they get AI assistance, they mitigate AI's bias in the decision process. They recognize that there is this potential of a biased decision here, and maybe we shouldn't do it. And like, I think I skipped that slide very quickly, but in counterfactual explanation for long prediction, for instance, we can, if a person can see that if the AI's prediction changes because of the race variable, if the person is Caucasian instead of African American, then he will get it wrong. Then maybe that would make the person skeptical of AI's decision and decide to override that decision. But how to do this appropriately, what the right way to do it, I think we are still at a very early stage in thinking about that.
Great question.
Great question, by the way. Thanks.
More questions? Feel free to raise your hand, unmute, go ahead. Yeah, Stephen, go ahead.
Okay, so this is a question for Allyson. So I am working on a natural language processing project, and I have been using the English model with Spacey. And I know there are other language models, but then earlier this year, I worked on a project where I used sign language. I tried to predict the sign that I am making, the gesture that I am making, so that the computer will recognize it and tell me what it was. So I want to know if there's work being done in the area of natural language processing to include sign language. So yeah, if you can tell me about that.
Yeah, it's a great question. It's really a very particular type of challenge to modality like that because of the fact, and as I was answering, the previous question, text is the primary medium that is used for these types of NLP models, followed by audio inputs for speech processing, and then processing visual inputs is a whole other type of challenge. And so we do have folks who have been working on that here at UChicago. A project led by Karen Levesque and Dan Brentari at TTIC and in Linguistics is specifically focused on that. And so they have been working on trying to improve the ability to recognize sign from video. And so I am not very well versed, by no means an expert in that project. I just know that they've been working on it, and I'm very interested in continuing work on that. But yeah, so such work does exist, but it is it brings with it particular challenges, because with text, you don't need to go through the process of recognizing what word it even is. You can just go straight to trying to map to hopefully useful abstract meaning representations and things like that. With sign, you have to go first through the process of trying to recognize what sign is even being presented in the input, and then try to map it to all the sorts of deeper, more abstract meaning things that we're trying to use to process meaning in language. So yeah, definitely some particular new challenges, but there absolutely are some folks who are working on it.
Thank you.
Good question, thanks.
Awesome, and actually we will get to hear from Karen Levesque in a couple weeks on a panel. So more NLP content to come. All right, we have time for a couple more questions. Yeah, Chimubi, go ahead.
Well, I guess I had another question for Allyson. Was there a specific reason you chose to use, or you guys chose to use Burt? I mean, because there are, of course, other ones. There's like Ernie and XLNet. Was there a specific reason to use Burt?
Yep. Yeah. I mean, it's a very simple reason. That's that I was writing this paper before those models existed. And so this was sort of early in the game when Burt was really the primary paradigmatic example of these new, very impressive pre-trained language models. And so a lot of people were asking questions about, or starting to ask questions about, what is it that this model really knows? It seems really impressive. We're not really sure what's going on. And so that paper is situated only a couple of years ago, or however long, but so much has happened in that time. So many of these new models have come out that at this point, this is a very natural question to ask, but at the time it was, there were a lot fewer of those models to look at. Subsequently, of course, a natural follow-up question to ask would be, well, have you looked at these subsequent models with these diagnostics? We have, to an extent. There have been certain challenges because of different types of different vocabularies that the new models have, different types of encoding of those vocabularies, and because of I'm trying to remember what all the different issues were, but you can still adapt the diagnostics to test them. And the basic pattern that we're seeing emerge, and this is roughly what I would have predicted at the time, is that for the first two diagnostics, we do see sort of incremental improvements. As the models get bigger, as they get trained on more data, they do get better at things like being able to recognize that spoon is the right answer in those sort of larger contexts where you need common sense, pragmatic or something like those types of knowledge, they do get better at being able to predict tipped when the waitress is doing the action versus served when the customer, the other way around, you know what I mean? Predict the correct event. But to the negation thing, which seems like more of a fundamental limitation of this type of pre-training paradigm, it seems like we basically see the same patterns. The models still tend to sort of ignore the negation. They still prefer the untrue continuation of Bird in association with Robin, rather than sort of preferring the true continuations in the conjugation. So that's the basic pattern that we see in moving forward in time to the newer models.
Yeah, thank you.
Yeah, good question.
All right, and I think we can squeeze in maybe one more question from Annie before we wrap up.
Yeah, okay, this is not really fully formed as a question, but for Allyson, I'm wondering, like, with machine learning and since a lot of it is like trying to predict the correct word, but with things like art and poetry, there's a lot of like unexpected combinations of words. So is there like work right now trying to like build this creativity into models, and how does that happen?
Yeah, absolutely. Great questions. Chenhao might be able to speak more to sort of creative use of language. This is an area that I have not been as focused on, because I'm focused more on sort of the nuts and bolts of trying to interpret meaning from any type of language. But I will say, in response to a part of what you said there, the presence of unexpected combinations that are nonetheless completely intelligible, I think, is a critical piece of information about the fact that simply predicting words in language is not the same thing as understanding language. Because of course, if I say something really unexpected to you, you can still understand it even if you didn't predict it at all. And conversely, you can also predict something without understanding it, right? I could say a bunch of nonsense syllables to you in sequence, and you could pick up on the patterns and predict them. So this is a point that I like to make frequently, and I think it's a really interesting and important one for the field at the moment, is that the fact that unexpected things often happen, and it doesn't mean that they can't be understood. This is sort of a critical property of language as well. Language, I can say something really bizarre to you right now, and you would never be able to predict it, but you'll be able to understand it because you're able to, understand language compositionally. So in thinking about evaluating how good these models are, we do need to tease apart their ability to predict things from their ability to really understand things if they're unlikely. So that's the point I wanted to make. Maybe Chenhao can say something more about if you know about what people are working on with creative language.
Yeah, I think in general, I guess there is indeed a growing interest in especially generating kind of say jokes and stuff and humor, and more, I guess, like creative writing is very broad. I think the community that is humor is almost distinct from the community who study, but I think there are communities studying both of those. And I think in space, I think I remember there was a paper 2 years ago kind of on modeling surprise and how you can incorporate surprise in generating jokes and so on. And more, I don't remember the specifics of that particular work. If you're interested, you can send me and I can try to direct you to that paper. But in general, I think in practice, in the end, most of statistical methods or statistical NLP in general are based on frequently patterns. So capturing surprise is very hard. And that's, I think, second, Allyson, what Allyson just said, I think is a kind of very fundamental challenge that we don't really know how to do. And I think the current paradigm is not really well suited for those challenges. And like, just to take the humor example, like, I think a lot of times people still need to rely on a corpus of jokes and find out what is common in a corpus of jokes. And that on its own, you kind of expand a surprise from general corpus, but it's not really a surprise if you are very familiar with jokes. And yeah, I don't think I know a good way to model it. And if you have a good idea, I would be happy to think about it.
Wonderful. Well, thank you everyone for these great questions, and to Allyson and Chenhao for joining us today. So let's give a virtual round of applause to them, and we will wrap up our speaker series for today.